Hey, welcome back to a new episode on the Web3 Idiot. I know I've been gone a bit. A lot of major life events has happened. I got a job offer, which is pretty great. I'll talk about it more later on. Just preparing for our first kid as well. So, sorry about the lack of videos, but we're back into it. Today we're tackling number 1038, binary search tree to greater sum tree. So this is a medium question. Given the root of a binary search tree, convert it to a greater tree such that every key of the original BST is changed to the original key plus the sum of all keys greater than the original key in BST. As a reminder, a binary search tree is a tree that satisfies these constraints. All right. The left subtree of a node contains only nodes with keys less than the node's key. The right subtree of a node contains only nodes with keys greater than the node's key. Both the left and right subtrees must also be binary search trees. So in layman's terms, this 4 is going to be turned into a 30 because this 30 represents the sum of all these numbers on the right-hand side. This one will become a 36 because it will be all the numbers. So 2, 3, 4, 5, 6, 7, 8, their sum would be this one. All numbers greater than this. And this 0 will become a 36 because it will represent all the numbers to the right as well. So we're going to come over here. We have a 4, 1, 6. Come over here. We're going to go with our lovely friend Excalidraw. So I think at the top we have a 4. It's way too big. All right, we'll go 4. All right, what else? We have 4, 1, 6. Go copy, paste, paste. 4, 1, 6. All right, so we're going to start off with this one here. And then in blue, keep that there. And then we'll do another one. We'll copy it over here. This will be what it will become. All right, and then let's draw some lines. Sorry, a little bit bad at drawing lines right now. All right, it's coming back to me. All right, and then, so basically we have, this one will stay a 6. This one will be 4 plus 6, which will become a 10. And this one will be 10 plus 6, so this one will be 17. All right, so basically what we're doing is we're passing this sum up to here, and then we're passing these sums to the left. So this 6 gets passed up to this 4. 4 plus 6 is 10. Then we take this 10, we pass it down. All right, so that's pretty straightforward. But the tricky thing is when we add another layer. So let's go ahead and add, let's see, we have 0, 2, 5, 7. All right, so here, we'll go ahead and copy these. 0, 2, 5, 7. Then over here we have 0, 2, 5, 7. Okay. So you have 0, 2, 5, 7. 0, 2, 5, 7. All right, and then of course we'll have our lines. So these are connected, these are connected, these are connected, and these are connected. Connected, 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 and connected. All right, so what's going to happen is we have this 7 will stay at 7, and then this 6 will be 6 plus any number larger than it. So this will actually become a 13. This 5 here will be equal to the 6 and the 7 added together, which, 13, 12. No, 13. What am I doing? So this 5 will be the equal to the 7 plus the 6, or it will just be equal to this node value here. So then we'll go 5 plus 13 is 18. Then this value is equal to all of these numbers together, the 6, 5, and 7, which is actually represented in this left node here. So this would become a, let's see. So this will become 18 plus 4, which will be 22. All right. Then we drop down here, and then we go right. This 2 here will be equal to the sum of this 4, 6, 5, and 7, or just this top parent up here, which will be 22. This one will be equal to this number here, which will be 23. And then down here we have a 0. 0 plus this number here, 23, will be 23. So this is how our new tree would look. And yeah, so something that you may have seen is we'll be passing down numbers to the left and passing up numbers from the right. So over here, basically what we're doing is we're passing down a 0. Then over here we pass down a 0. Over here we pass down a 0. And then down here we get a 0. So this is our null will break out. We'll pass up a 0. 7 plus 0 is a 7. Over here we'll pass down a 7. All right. And then it will be 7 plus 0. So once we hit a null, we'll pass this back up, and then this 7 here will actually come up to this 6. So then this over here will be 7 plus 6, which will be our 13, and that will be the number we pass down. And then here, that's when it becomes this 18. So on this side, we'll pass down an 18. No, sorry. No, this side we pass down a, we pass down a 13. And then on this side, we pass down an 18. And then, so when we hit this base case here, this 13 will be passed up back here. Will be added to this 5. To get the 18, we pass it down to the left. This 18 will be added to the null value of 0. And then this 18 will be passed up and then passed up again. So now over on this side, we have 18 plus 4. So that is the value that we've passed up and is now being passed down. And then same thing over here, 18 plus 4. And then here, so we'll just change this to 22. And then left side we pass down 22. Okay, we break out, we pass it back up, we add it to this 2. Over here we get 24. This is the number we pass down, 24 plus 0. All right, then we pass it back up to here. This is 24 plus 1. I'm sorry, I'm trying to be as clear as possible, but I know it can be a bit confusing. We'll pass this down. Over here we have, oh yeah, what am I doing? It should be 24, 25, 25. Oh, sorry about that. All right, and then this 24 plus 1 will be passed down to here. So this one on the left will be 25, then plus 0, 25, and we are left to that. So, all right, this may not make as much sense as I wanted to do, but we're just going to go ahead and maybe if I code it out for you, it will make it a bit more sense. So this is going to be a recursive approach. So we're going to be using, I like to call them helper. We're going to be passing down a node, and then our cumulative sum, the right-hand sum that we'll be passing down. And then basically what we're going to do is say if there's no node, so if we've broken out, what we're going to do is return our sum. And then what we want to do, according to our graph, is we go right first, because we're going to be adding up numbers that are greater than the node. So we're going to go ahead and say let our right value equal to our helper. This is where our recursive call comes. of our node.right, and we're also going to be passing down our sum. We're going to get a new value that we'll be changing this node to. So let our, we'll call it new val, is equal to our node.val, and we're going to be adding this to the sum that is being passed up. So this will be the equivalent of the number that we're passing up, which would be this right. And then what we want to do is say node.val. We are updating it to our new val. You could probably skip this step and just make it one line, but I want to keep it separate. And then we're going to go left. So our left is equal to our helper of our node.left, and we're not passing down this sum. We're going to be passing down this value here, new val, because that represents all the numbers that are greater than the left-hand side of our node. So that is our parent, and then our parent's right children. And then at the end of this, what we want to do is just return our left, because left will be the accumulated number. So that would be this 26 that gets passed up here. So this 21 here, the 6, which is actually turned into a 21, will pass up this 26 over here, the left-hand side, and up to this 4. And then from there, what we want to do is call our helper on our root, and we're starting at 0. And then finally, we will return our updated root. We'll go ahead and run it, see if it works. It does work. All right, let's submit it. Hopefully we are okay. 65%. Okay. Let's go ahead and jump into time and space complexity. So our space complexity will be O of D, where D is the depth of a tree, because that is representing the call stack in the recursive. So over here, so we have 1, 2, 3, 4. So this 4 represents the lowest level. So we just have to keep track of 4 calls. So that would be the O of D. Worst case scenario is O of N, where it's a completely one-sided tree, where it's all right children. So we'll go ahead and just call space O of N. And then our time complexity will also be O of N, because we have to hit every single node in order to calculate the numbers. So O of N space, O of N time. You could probably do better with the space, but for me, this is the most straightforward way of doing it. And especially if you understand recursion, it makes a lot more sense. So hopefully this explanation did not confuse you too much. I'm sorry if it did. It's been a while since I've done one of these videos, and I'll continue to improve. Be on the lookout for more videos this week and next week, and hopefully until I start my job. I'm unsure if I'm allowed to continue, I guess, making these videos with this new job, but I'll figure that out, and hopefully we can continue and helping you guys. Anyways, thank you so much for your time, and I hope you enjoyed this, and I hope you've learned something.